to compute the gain, which means the entropy of the parent node and the entropy of the partitions, you take the difference. And it can be proved that actually this difference would be always either 0 or positive. And in fact, they will lie within the interval of 0 to 1 in this particular case. So this is the gain that you just know. I have scribbled and it is abstracting, but I hope you can read it. It is 0.395. That is the gain. That is the gain from the attribute A1. Similar computations you are doing with A2. The same computations you are doing with A2 attribute, and you find the gain is 0. So there is no gain. It has almost equally split all the examples. So for this kind of, in this case, naturally the attribute A1 should be chosen for the split. And that is the step in the decision tree building, that you consider the node, parent node, where the test should be done on attribute A1, and you create two descendants or child nodes by creating those partitions. And since you see that both the nodes they are not pure, that means they got a mixed mixed levels in their distribution, in their set of instances. So that's why you need to again apply the same rule of splitting it by considering the gain in information or reduction of the entropy values due to partition. So you go on doing these things till you get leaf nodes. You get leaf nodes of same classes. So at the worst case, it may come that every leaf node will have only one instance. At the worst case, that's why theoretically it is possible to build up a tree which is consistent. You can satisfy every 10 examples. The other examples also I mentioned, so let us not repeat. Let me then proceed in this case. So the gain function that I discussed, that I mentioned, that it's a measure of reduction of uncertainty, and its value lies between 0 and 1. Here, when you have a two-class split, and I mean you have two-class levels, and then the significance of it here, particularly for this example, gain of 0 means, as I was mentioning, that 50-50 splits of both positive and negative examples in the partitions. And gain of 1 means actually you have completely separated out these class levels into two partitions. So you have the perfect certainty after splitting of leveling the classes. And naturally, what you are trying to do, you are observing the patterns, or I should say class distributions, given the attribute values, and from there you are taking a decision based on certain statistical measures like entropy, and you are moving to the locally minimal representation of keys. That means you are going more and more to the regions of homogeneity, sets of homogeneous sets by splitting, and that's how you are reducing the overall entropies if you consider the aggregated entropies of all partitions.
Sir?
Yeah.
Sir, can entropy gain be negative?
No, it cannot be. Entropy cannot be negative. From the definition, you can see.
No, sir, entropy gain.
Entropy gain cannot be negative. That is also it can be true. See, it's a kind of, you are getting more ordered set whose entropy will be, overall entropy, that means aggregated entropy will be less. You are imposing more ordering. Okay, there are mathematical proofs, you can go through them. So, but it cannot be, gain should be always either 0 or positive. This is the training examples that was given, and again I am showing you this set of examples. As you can see that you have 14 instances, training examples, and there are 4 attributes: outlook, temp, humidity, wind, and you have 2 classes, which is then you are going whether you are going to play tennis or not, and the answers could be 2, either yes or no. So that means there are 2 levels. So with this data set, let us again uh, rerun the exercise. That means to form a decision tree. So how many, what is the class distribution at your hand when you are at the root node? How many positive examples and how many negative examples? Can you count and tell me?
Sir, 5 negative, 9 positive.
Yeah. So 9 and 5, right? So what should be the entropy? Entropy of this class distribution. So when you say entropy, you should refer entropy of what? Right? So entropy of class distribution, that you should keep into mind. It is not entropy of outlook. It is not, see, every attribute will have certain probability distributions in the attribute space, and it has certain entropy there. And you can consider entropy of the whole instance space also in that way, if you have the joint probability distributions of the attribute space. But no, what is being considered in the formation of decision tree, it is the class distribution. It is the level distribution. That means the output of the target functions, distribution of the values of the output, values of the ranges in the target function. Right. So did you compute the entropy of the of this class distribution of the given training examples?
0.9.
Okay. It's not exactly okay. It is saying it has started. Yeah, fine. So it is saying 0.940. Is it wrong?
Sir, it's correct.
No, sir.
It's correct, no?
Correct.
Okay. So here, as you can see that no, it has selected humidity because no, not selected. I should say that if you consider the attribute is humidity, then the entropy distribution in its partitions, rather the entropies of each partitions are like this. So if you consult the training examples, you will find that with the value of humidity high, there are 3 positive examples and 4 negative examples. Similarly, with the value of humidity as low, there are 6 positive examples and 1 negative examples. So naturally, you can understand the second one will have low entropy because you have a very skewed data, whereas the first partition will have high entropy. So it is 0.9. See, you see that entropy of the partition is higher than the entropy of the original set, but the overall entropy of the aggregated partition would be lower. Okay, because you have also sufficient reductions in the other set. And if you take the overall entropy, what should be the overall entropy? How do you compute it? It is basically 50-50, 50-50 split. 50-50 in the sense of number of instances. 7 plus 7. So it is the average of these two. Is it clear? Is there any question? Okay. So you take the average of these two, and no, if you take the average and if you compute after that the gain, that means 0.940 minus average of 0.985 and 0.592, the gain will come as 0.151. Now this is for humidity. There are other 3 attributes. So I think let us proceed. This is for wind. And here you can see here you have entropy 1 because you have equal number of positive and negative examples. That is the highest entropy of with this kind of class distribution. And here the gain is 0.048. Similarly, if you carry out this exercise, which is not shown, these distributions, you will find that using Outlook or using Sky, I mean, in my tree structure, I use the attribute name Sky, but no, Outlook is also another name, just the name. There the gain is 0.246. With temp, it is 0.029. So which one you should select out of these 4 attributes?
Outlook.
You should select Outlook. Okay. So if I select Outlook at the parent node, which is incidentally is a root node, because this is the start. This was the starting point. So now I have to propagate my sample set or instance set into 3 branches, because you know that Outlook had 3 attribute values. It has 3 attribute values like sunny, overcast, rain, and it has partitioned the space, instance space, or rather I should say training examples, not space, training examples into 3 sets given the Outlook value. And you can see the class distribution. The leftmost 2 positive and 3 negative. I have not marked which one is positive, etc. You can consult the table given to you with the list of training examples. Then the middle one, 4 positive, 0 negative, and the rightmost subtree, that means rightmost descendant in the diagram, it is 3 positive and 2 negative. So you can see in 4 positive and 0 negative, there is a level called ES in the diamond enclosure. So why it is so? Can you tell me? Why I have put ES here and other 2 as question mark?
All
Cause
examples
all
are of one class.
So
Yeah.
don't
So
need
this
any
is
more
a
class.
pure node. This is a pure node. Huh? So you do not split it. You just give the level. So the level of the instances, because all are having same level. So you level that node by the level of the instances. So it's a positive levels, which means yes in our case. But you need to split the corresponding nodes where you have mixed levels. Right? So what should you do in this case? You should follow the same policy. So first you should compute the entropy of the data. Suppose I consider the branching using sunny. That means I consider the corresponding node which is connected through the edge sunny. So what is the entropy there of that node? What should be the entropy?
Point 0.97.
0.97. So you computed, no? It's just 2 by 5 log of 2 by 5 plus 3 by 5 log of 3 by 5. Then you negate it. Okay. So if I do it, I mean, this is a sunny, it's just explained. It has 0.97, for example. And then you have to consider all possible attribute values once again. Like use sunny, use outlook, use humidity, wind, temperature, and check the corresponding entropy, aggregated entropy of their partitions using their values. And here, you will find that actually I have not used sunny here, though you should also, I mean, I have not shown, but you should also see the gain using sunny there also. So you find that if you carry out this exercise, so which one is the highest gain? That is gain corresponding to humidity. Okay. You see the gain is quite high. It is 0.970. That means humidity is going to give this complete split. So humidity is actually giving you two pure nodes. That's why you have computed 0.97, so which means the aggregated entropy will be 0. Is it clear? Similarly, for wind also, you will find the same thing. It has happened so, given these examples, it has, it has become like this. So this is your final decision tree for the example. Any question at this point? Okay, so let me proceed. So this, based on this algorithm, there is an algorithm called ID3. That's the name of a standard decision tree algorithm, which follows this kind of principle. And there are, of course, some other principles are there, but mostly this principle. And it is searching a hypothesis space, but the search is a greedy search. That means you are forming a particular hypothesis, but you are trying to split it in such a way that you greedily try to achieve a minimum tree. Though it's a greedy approach, it is not really. It's a it would be the global minimum. It is actually try to get a local minimum configuration of the decision tree. So one of the interesting thing about the hypothesis space is that it is complete. I mentioned this already in my first lecture itself on decision tree, that because of this kind of general expression, form of Boolean expression, that is disjunctions of conjunctive forms, it's a it is complete. It includes all possible Boolean expressions, and the target function in the form of Boolean expression will be included there. And this is the kind of principle. It conducts a search of the space of decision tree, and so goal is, of course, to find the best decision tree. But as I mentioned, that finding a minimal decision tree consistent with a set of data is NP-hard. So there you perform a greedy heuristic search, and it is hill climbing without backtracking, which means that it is just going into one direction only. And once you get the answer, that is kind of local optimum in that particular direction. So it is a statistics-based decisions using all data. And once again, I think this is a kind of summary. It is complete and target function included, use gain, whatever I have said, it's mostly the summary of that. Cannot assess all hypotheses. So this is another thing it is trying to hammer, that you get only one consistent hypothesis. It is not that you are computing a version space using candidate elimination algorithm of the previous topic of concept learning. So decision tree is also kind of concept learning, but no, it is more powerful representation. But see that you are not computing it is not giving all possible hypotheses, consistent hypothesis. So it's kind of, you are doing breadth first search as if you are going towards directions where all trees at a given depth, and you are choosing the best and go to that directions. And no backtracking means you are trying to get the locally optimum solution, and just statistics-based search choices. So one interesting comparison with respect to the previous approach of concept learning, where we have used algorithms like candidate elimination, and the kind of representation of hypothesis that we took, which has restricted the hypothesis space. As you can see that all possible expressions were not considered in the hypothesis formations. So you have certain kind of restriction bias. So certain subset of all possible expressions, those are considered as your hypothesis space, and that is a restriction bias. There is also another name. It is as if it's a language bias. Like in language, you do not consider all possible combination of words they form a sentence. So there is a bias. There is a rule. There are rules by which the sentences are formed, by using those syntaxes. We speak our our speech, or our that's the way we speak, that's the way we write. So, so that's why it is also a restriction, and that is called language bias. But the thing is that it is giving an incomplete hypothesis space. On the other hand, the search-based technique, you have a preference towards certain set of hypotheses. You are characterizing them, and you are choosing no certain hypothesis in preference to the others, and that makes your search strategy also incomplete. So, in this case, your search is incomplete. It is not complete search. Uh, like candidate elimination has restriction bias, whereas this particular algorithm, which is ID3, that's the name of the algorithm, what I discussed so far, the best principle I discussed, and that has more preference bias. And in most cases, we have both a restriction and a preference bias. So in actual real life, when you design machine learning algorithms, you will see a mixture of this both. Let us also discuss that what are the inductive biases that we considered in this particular algorithm of decision tree, and which we name it as ID3 here. So one of the things I mentioned already that you are preferring shorter trees, and because you are choosing the high information gain attributes, and from the root itself you are trying to do. So you try to keep your split, try to make your split as homogeneous as possible at every stage, and in this way you are trying to restrict the growth of the tree. So it's a principle of Occam's razor that you have applied. So you are preferring simpler hypothesis. If I say the size of the tree is the complexity of the hypothesis, so by restricting the growth of the tree and its depth, we are preferring the simpler hypothesis in that case. So that is what shortest hypothesis that fits the data. So what is the justification in this case? So it is that smaller likelihood of a short hypothesis fitting the data at random. So the problem is that whether your hypothesis is somehow by chance, it is randomly, it has fit the data, and which means that if you consider any unseen examples, most likely, again, it is not going to label. I mean, it's kind of random choice of output labels there also. So that randomness will be there. So, but no, if you have shorter hypothesis, then that probability of selecting that kind of random hypothesis will be less. But the problems is that, of course, there are other ways to reduce random fits to data. So it is not the only criteria that you can consider, and your size of hypothesis based on the data representation. It's a kind of data dependent. That's what it is trying to say. You are applying minimum. So I think these are other principles are also there. We'll come to some of them. Now another thing you should consider that, like, while getting a consistent hypothesis, you are also taking a risk of overfitting the data. Suppose you grow the tree and till the end of getting all nodes as pure nodes, but if there is a noise in the data, then naturally some of the growth, some of the splits are also erroneous, because you are led by those erroneous level, and so those splits will cause error in actual while applying it in the unseen levels. And you are also having smaller observation data, so that would amplify the scenario. That means any small in a small data, if you have some noise, and if you try to fit it so that you make it error free, but actually there will be a lot of errors because of that, and disturbance could be quite high. So it is not that a small amount of error, only a single erroneous data will not. I mean, the effect may be very significant. That is what my point. It is difficult to say, but it would be significant. So the overfitting is a concern here. That means that is what is a definition of overfits. Already I mentioned also earlier that it overfits the training data if there exists another hypothesis H prime such that it has greater error than H on the training data, but smaller error on the test data than H. So this is a very direct and naive definition. So you try to understand that I say it is overfitting this hypothesis because I consider there exists. So if there exists, so it is not that no in probability. I say that no, there is an hypothesis which may give larger training error. So that's why you did not choose it, because you have considered no, the minimization of training error, and of course in this case making it 0. So that hypothesis will never be chosen in preference to this one unless no, if it is some kind of that, as I told you, ID3 has certain preference bias. So in that direction, if that is the local minima, otherwise no, you may not get that hypothesis in its neighborhood if it lies in its neighborhood. And but no, in the test error, in the test data set or in the generalized data set, it has minima, it has less error. Then we say this is a case of H is an overfitting. So a kind of a graphical representations, what would happen if you are going to get the training overfitting cases. You can see that accuracy, it is not error, it is just the opposite. Accuracy of your class leveling or classification, accuracy of your classification. So with the training examples, this accuracy is increasing. Accuracy is increasing, and with training error, actually accuracy will be 100%. With a consistent hypothesis, accuracy will reach at 100%. Whereas if I consider when you are forming the hypothesis, you can take the hypothesis formation, you can choose hypothesis and some consistent hypothesis where it would be like this. But no, you will find at some point actually though you are getting more and more consistent hypothesis, you are reducing more and more training error, and you are increasing the accuracy. In actual test cases, accuracy is going to decrease, and this is a very ideal scenario when actually data overfits take place. So there is one nice visual example. We have considered this kind of decision tree formation with this visual example. So we have explained that in this case you have two-dimensional instance space. It has two attributes, attribute 1 and attribute 2. And what is being shown here graphically, that the points where there are positive examples and there are negative examples, those are the positions where you have positive instances and negative instances. And you had the tree already formed where you can see, let me use the pen. So if you remember, so this was the first split. That means this is the root node which will have its descendant into these two regions, and this split takes place with attribute 1, right? In the decision tree, this tree takes place at attribute 1. This may be some value, say x. So the decision tree will, in the decision tree, you check whether attribute 1 is greater than x or less than x, depending upon you move towards left or right of the tree. Then, one of the node has become, of course, pure. So you don't move after that if it happens. Otherwise, no, you go to the other node. Suppose it is the left node, and there also you get a set of levels, instances, and these are mixed. So here also you have another split, and this is also split over the attribute 1. So this is the split, and suppose this value is at y. Once again, you get two nodes. One node has become eventually pure node, and the other node is a mixed node. So you go on splitting it, and now you are splitting with the attribute 2. Suppose this value is z, and you get two regions. In the previous example, actually, this example was positive. So we stopped there. Did you remember? You stopped there. So you have only two leaf nodes after this. So you stopped, and no, this is the decision tree. That was fine. But suppose it is negative, as it is shown here. So naturally, again, you have to do some splitting in this domain. In this node, you have to do again splitting because of this, because to make it this hypothesis consistent, and that would cause overfitting. So you may assume that this is an erroneous example. So let me proceed with my arrow. So now you require a very deep tree to fit just one odd training example. That is the problem of overfitting. So I can show you that what happened if you go on doing this kind of splitting. After that, you can see that you have many splits. Probably, as you can see that probably I'm not sure, but maybe say this is the next split. You have two regions. This is pure region, but this region is a mixed region. So you have, say, next split here. Once again, this is a pure region, and now this is to be split, and maybe here you have three splits. I mean, since it's continuous value, you can do that. You can take three discrete intervals and you can split there in three partitions, and you can stop there. So you can see that at least you have three more splits I mean, the depth is increased by another, I think, 3, right? So that is, of course, consistent with this set of instances. But as you understand that in reality, if it is a noisy sample, then it's a lot of error. It may introduce quite a bit of error. So these are the things that adding noisy trainings. Another examples we are showing here. So that was the visual exam. Visually, we show you some kind of effect of a noisy samples over that rectangle hypothesis, formation of rectangle hypothesis. Now, let us consider our training examples which we took earlier. And let us assume that we had 14 examples earlier. As you remember, let us have an additional example. And you see that additional example is sunny, hot, normal, strong, no. Now this is a new example we assume, and there we can find out from the attribute values that probably this is an erroneous. I mean, you can understand that, of course, when your machine is computing, machine has been told that every example is fine. You have to get a consistent hypothesis. Machine will not distinguish. But you can see, as per our understanding of our sports playing, that it's a good condition. Outlook is sunny, temperature is hot, humidity is normal, wind is strong. Maybe temperature hot may have some issue, but no. Let us see the tree. So if you consider the previous tree, and if this example was not there, what would have been the level? If this example was not there, what level it should get? Suppose this.
No.
Yeah. Suppose this no is not here as a label. suppose only you get this instance. So what should be the class level using this
Yes.
decision
Yes.
tree? Class level should have been yes, right? But now you got no. In your training example, you got no. So naturally, this tree needs to be modified. And just because of this example, now there could be in various ways this could be modified. But one such consistent formation could be that this one, right? If you use those data once again, suppose you include it, and maybe this is one kind of formation. So you see that it has increased the depth of the tree, and it has also considered this case, and you can see that it will be because wind is strong, humidity is normal, wind is strong. It has not considered temperature as I could see from the attribute yeah, space decision in this node, and then it took no and yes. Actually, it could take also temperature. It doesn't matter. Only it depends on as you understand. It's not an unique answer. So this could be a tree which is consistent with the training examples, but as you can see that it will wrongly classify that example as no if you consider that was is a noisy data. And not only that examples, for many other examples also it will have some issue. So what are the strategies by which you can avoid this overfitting? Now, there are two basic approaches. One approach is that you can perform pre-pruning of the tree. That means you restrict the growth from the very beginning itself. So before growing the next node, you just have certain kind of test, and you don't grow. You consider, okay, fine, we'll stop there. We'll accept that error at that stage. We accept that error. So we are happy with that kind of training error because there is a risk of overfitting. That is the kind of pre-pruning strategy. Whereas post-pruning strategy is that you grow the tree, get the consistent hypothesis. Now you check from the bottom. From the bottom, you check that every node, intermediate nodes, whether if we remove that node, whether that improves your generalization error. I should say validation error. So you have those validation. I told you that how do you select a model? It is also selecting a model. So you can have training set, validation set, test set, and suppose you are growing the tree, selecting the hypothesis based on training and validation set. So post pruning will be helpful there. So you can just find out that after pruning, whether it is improving your validation error measure. That means it is reducing validation error. So you allow pruning. So this kind of strategies, there could be various others. So let us see. So pre-pruning, as I mentioned, you stop growing the tree at some point during construction when it is determined that there is not enough data to make reliable choices. And post-pruning, it is growing of the full tree and then removing nodes that seem not to have sufficient evidence. I explained a little bit just before, and it happens to be it is more popular. Now, all these comments are from Professor Pavitra Mitra, so I'm using his slide. So no, I believe him, and I'm making these comments. So this is evaluating subtrees to prune. So there are different methods of evaluation. As you can see that I mentioned that you can have cross validation, you can have statistical testing, you can have minimum description length kind of evaluation. Cross validation I explained. I did not explain statistical testing, which will be discussed in my next topic. And minimum description length, we'll see. It will come. It may come. Or maybe during hypothesis testing, statistical testing, we'll see. So cross-validation, it is already, just I mentioned earlier also, that you make a training set and validation set, and you evaluate based on your validation error. And whereas you can make also k-fold cross-validation. That means it is not necessarily that you have to use the same training set and same validation set. Rather, you can partition the instance examples into certain folds, k number of partitions. Take k minus 1 part, any random k minus 1 partitions as your um, training set, and the other partition as validation set. Do it, and finally, you consider the average of them. So this is a kind of also k-fold validation. Statistical testing would be that it is kind of test which observes whether the hypothesis that you are going to refine. That means that node, whether when you are going to prune, whether it is just by chance, or whether it has some kind of I should say associationship, or some reason, good explanation that actually it is not random. It has some justifications, statistical significance, we say, with respect to that kind of pruning. We'll explain during hypothesis evaluation. That is also a topic we will discuss. And the minimum description length is this. See, you are reducing the length of your hypothesis. Now, when you reduce this length of your hypothesis, then you are also, which means that you are not considering some of the exceptional cases, and you are just simply removing them. Now consider a rote learning kind of strategy. Of course, it's not purely rote learning. The idea is that suppose those exceptions are specially kept in some lookup table kind of scenario, and every time before applying hypothesis, you just go through that exception list. If it satisfies, if it is included, then you take the decision, and then you go for hypothesis. Suppose you do this thing, what is the size of storage of that list of exceptions and size of your pruned hypothesis? Now, if this size, or sum total of this size, is less than the total size of the old hypothesis, which has also taken care of exception, then you should go for the second case. So these are the cases. So maybe I will stop here today. I have almost come to the end of this class, and I have to take attendance today. I could remember. So first, let me take attendance, then I will take your questions and discuss other things. Okay. Attendance is taken. Now, I need to announce a few things regarding your assignments, and I will also take up your questions. So one thing, let me explain that a few of you just sent me mail, approached me that you have some difficulties in developing codes of building trees, etc. Because we asked in our assignment that you have to build the decision tree on your own. You cannot use any standard package where already if you give the training examples, they will give you a tree, because you are learning. So that's what we want, that at least you should form one decision tree on your own. You should write that code. Now, if you are not really able to do it because of some limitations, etc., of your background, so what we consider that that 20% marks will be deducted straight if you do not write that code of tree reconstruction. Otherwise, all your rest of the assignment, part of your assignment, which you can do by getting a tree, that would be evaluated on 80%. So that is the kind of decision we have taken. So you may choose what you want to do. Okay. So now, if you have any questions, let me know. So it seems all good. No question. Okay. So in that case, thank you very much. I'm stopping the recording also.